Bismillahirrahmanirrahim. Assalamu alaikum. Welcome, my dear students. I am Muhammad Arifur Rahman, lecturer Mathematics Department, Kumilla Government College, Kumilla. Today, we will discuss about Honours Third Year course Abstract Algebra, Chapter 1, Relations. Today, our class 1. Dear students, we will discuss about ordered pairs. Given any two elements A and B, we write A, B to define an ordered pair with A as the first element and B as the second element. Dear students, here A, B, first bracket and second bracket are different. One is ordered pair and the other is set. Secondly, A, B is not equal to B, A unless A and B is equal. But the set A, B is equal to B, A. The set is equal, but the ordered pair is not equal. With the ordered pair A, B, we denote a point in Cartesian xy plane whose abscissa is A and ordinate is B. Dear student, now we will discuss about Cartesian product. The Cartesian product of two sets A and B is the set of all ordered pairs forming with the elements of A and B. It is denoted by A cross B. So A cross B is equal to xy such that x belongs to A and y belongs to B. Let us discuss an example. Let the set A is 1, 2 and B is 3, B. So A cross B is 1, 3, 1, 5, 2, 3, 2, 5 and the set is B cross A is equal 3, 1, 3, 2, 5, 1, 5, 2. This shows that A cross B is not equal to B cross A unless A is equal to B. Now we will discuss Theorem 1. Theorem 1 denotes for any three sets A, B and C, prove that A cross B union C equal to A cross B union A cross C. Let us discuss about the proof. A cross B union C equal to xy such that x belongs to A and y belongs to B union C. We can write y belongs to B union C as y belongs to B or y belongs to C. Dear students, we know that if there is union, we can write or, and xy such that x belongs to A and y belongs to B or x belongs to A and y belongs to C. We can write the term as xy belongs to A cross B or x belongs to A and y belongs to C. We can write xy belongs to A cross C. Now we can convert the or as union, so the proof is completed. I hope all of my students understood this proof. Dear students, we will discuss about the definition of relations, which is the name of our chapter 1. Relations. Let A and B be two sets. A relation from a set A to a set B is a subset of A cross B. It is denoted by R. Thus R is a subset of A cross B, that is xy such that x belongs to A and y belongs to B. If AB belongs to R, then we say that A is R related to B. If AB does not belongs to R, then we say that A is not R related to B. In other words, A is related to B if and only if AB belongs to R, and A is not related to B if and only if AB does not belongs to R. The empty set phi and the set A cross B are the subsets of A cross B. The phi is called the empty or null relation and A cross B is called the universal relation. I hope all of my students understood this discussion. Let us discuss about an example. Let R is equal to xy belongs to n cross n such that x equal to 3y. Then R is relation, R is subset of n cross n, which means R is relation on the set n. It is clear that R is equal to 3, 1, 3, 6, 2, 9, 3, 12, 4, 15, 5. We write 3 is related to 1, 3 is related to 1. My dear students, we see that 3 is related to 1, 6 is related to 2, 9 is related to 3, 12 is related to 4, etc. Let us discuss about binary relation. Let A be a given set, then a subset R of A cross A is called a binary relation. It is simply called a relation in A. Let A is equal to 1 to 3. So A cross A means 1 1 1 2 1 3 2 1 2 2 2 3 3 1 3 2 3 3. Let R is equal to 1 1 1 3 2 1 3 2. Then R is a subset of A cross A and R is a relation in A. Now we will discuss about inverse relation. Let R be a relation from a set A to a set B. Then the relation R inverse from B to A is called the inverse relation of R if and only if R inverse equal to y, x such that xy belongs to R. Let us discuss about an example 4. Let A is equal to 1 to 3, B is equal to AB. Then A cross B is equal to 1A, 1B, 2A, 2B, 3A, 3B. Let R is equal to 1A, 2B, 3A. Then R is a subset of A cross B. And so R is relation from A to B. So R inverse means A1. My dear students, we see that R is equal to 1A, 2B, 3A. Then R inverse means 1A, which is R1A belongs to R. Then R inverse means A, 1, B, 2, A, 3. Every relation has an inverse relation. I hope my dear students understood the discussion. My dear students, let us discuss about composite relation. Let A, B, C be any three sets. Let R1 be relation from A to B, R2 be relation from B to C. Then the relation from A to C is called the composite relation. In other words, R1 is a subset of A cross B and R2 is subset of B cross C. Then the composite relation R2 is related to R1 from A to C is defined as R2 composite relation R1 is equal to A, C for all there exists B belongs to B, there exists AB belongs to R1 and BC belongs to R2, which is the composite relation. Now we will discuss about types of relations. My dear students, a relation R in a set is said to be reflexive if AA belongs to R for all A belongs to A, symmetric if AB belongs to R, then BA belongs to R, transitive if AB belongs to R and BC belongs to R, then AC belongs to R, and asymmetric if AB belongs to R and BA belongs to R, then A is equal to B. My dear students, now we will discuss about equivalence class, which is equivalence class. Let R be an equivalence relation on a set A and A belongs to A be arbitrary. Then the set of all elements of A that are related A, that is X belongs to A such that X is related to A subset of A, is called an equivalence class of A determined by A and is denoted by A or A bar. That is A third bracket is equal to A bar is equal to X belongs to A such that X is related to A, which is subset of A. Similarly, we define B bar, C bar for BC belongs to A, the family consisting of all equivalence classes A bar, B bar, C bar of A is called the equivalence set of A with respect to the equivalence relation R and is denoted by A bar is equal to A divided by R, Thus, A bar is equal to A divided by R is equal to A bar, B bar, C bar, etc. I hope all of my students understand the discussion. Dear students, we will discuss about partition of a set. Let A be a non-empty set and delta be an index set. Then the family of non-empty sets is called partition of A if A is equal to union of R belongs to delta BR. For any BQ, BS is subset of PR, R belongs to delta, implies either BQ is equal to BS or BQ intersection BS is equal to phi. Let us discuss an example. Let A is equal to 2, 3, 5, 7, 9, 11, 13, 17. B1 is equal to 2, 3, 5. B2 is equal to 7, 9. B3, 11, 13, 17. B4, 7, 9. Delta is equal to 1, 2, 3, 4. Here, A is equal to union of R is equal to 1 to 4, BR. Secondly, B1 intersection B2 is equal to B1 intersection B3, B1 intersection B4, B2 intersection B3 is equal to 5, and B2 is equal to B4. The family of sets BR determine a partition of the set A. Dear students, we will discuss about the properties of equivalence classes. Here is in Theorem 2, let R be an equivalence relation on a set A and A denote the equivalence class determined by the element A. If AB belongs to A division R, then A belongs to A belongs to B, if and only if A is equal to B, A intersection B is equal to O, phi, or A is equal to B. That is, the equivalence class determined by two elements are either disjoint or identical, or any two equivalence classes are equal or their intersection is empty, which is the theorem. Now we will discuss about the proof. Given R is an equivalence relation, so it is reflexive. We have A is related to A for all A belongs to A, which implies A belongs to A for all A belongs to A. Secondly, let A belongs to B, then A is related to B. Thus, any X belongs to A if and only if X is related to A, if and only if X is related to A and A is related to B by given condition, if and only if X is related to B. Thus, R is transitive if and only if X belongs to B. Thus, A is equal to B. Conversely, let A is equal to B, then by 1, A belongs to A, which implies A belongs to B. Thirdly, if A intersection B is equal to phi, then there is nothing to prove. If A intersection B is not equal to phi, then let X belongs to A intersection B, which implies X belongs to A and X belongs to B. Which implies X is related to A and X is related to B. A is related to X and X is related to B. Thus, R is symmetric, which implies A is related to B. Thus, R is transitive, which implies A belongs to B, implies A is equal to B by given condition 2. Thus, either A intersection B is equal to phi or A is equal to B, which is our proof. Dear students, now we will discuss about congruence modulo or relation, which means congruence modulo, which is an important topic on abstract algebra. Let A be are any two integers and M be a fixed positive integer, then A is said to be congruent to B modulo M, denoted by A is congruent modulo B if and only if A subtraction B is divisible by M, that is A minus B is equal to K into M, where K belongs to Z. That means K is any integer. Let us give an example. 17 is congruent modulo 2 with modulo 3, since 17 minus 2 by 3 is equal to 5. There is a problem. We will discuss about a problem. Prove that congruence modulo 3, that is congruent modulo 3, is equivalence relation on Z. Here is the proof. From the definition, we know that A is congruent modulo B with modulo B M if and only if A minus B is divisible by M, which implies A minus B is equal to Km, where K is in integer. A is congruent modulo B with modulo M if and only if m minus b is divisible by m, which implies m minus b is equal to k into m. Now we will discuss the check the reflexive, either the relation is reflexive. For each a belongs to z, we have a minus a is equal to 0, which we can write 0 as 0 multiplication with 3, which implies a is a with congruent modulo a with modulo 3. The relation congruent modulo 3 is reflexive. Now we will check the if the either the relation is symmetric. For any AB belongs to Z, let A is congruent modulo B with modulo 3, which implies M minus B is divisible by 3, which implies M minus B is equal to 3k, which implies B minus is equal to 3 into minus k, since k belongs to Z, which implies B is congruent modulo A with modulo 3. The relation is symmetric. Now we will discuss either it is transitive. For any ABC belongs to Z, let A is congruent modulo B with modulo 3 and B is congruent modulo C with modulo 3, which implies M minus B is equal to 3k and B minus C is equal to 3l, where k and l is belongs to Z, which implies M minus B plus B minus C is equal to 3k plus 3l, which implies M minus C is equal to 3s, where s is belongs to Z, which implies A is congruent modulo C with modulo 3. The relation 3 is congruent modulo 3 is transitive. Since the relation congruent modulo 3 is reflexive, symmetric and transitive, so the relation congruent modulo 3 is an equivalence relation on Z, which is our hence the proof. My dear students, thank you everybody for attending my class. I hope everybody will stay safe, stay home and continue our studies. And everybody, thanks to everybody.